Welcome to the data mining lesson video on subset selection. In this video, we're going to talk about subset selection, which is a process of selecting a subset of your regressive variables to be used in multiple linear regression. So why do we want to use a subset of the regressive variables instead of using all of them? Well, for one thing, good subset selection improves prediction performance. And so this makes sense. It's not hard to understand. If you have, say, 10 regressive variables, 5 of them are useful for predicting your output and 5 of them are just random unrelated variables, then trying to work with all 10, you're not going to estimate the coefficients for those 5 irrelevant variables as 0. You're going to have some non-zero coefficients estimated for those, most likely. And then you'll wind up making predicted values that are based on things that are not relevant for your outputs. So clearly, good subset selection can improve prediction performance. Also, good subset selection improves model interpretability and statistical inference. When you remove variables that are not relevant for your output, it helps you to understand what's related to your output variable and what isn't related, or what's not related in the presence of those other variables that are more useful. It also allows better estimates of the coefficients. So let's look at a process of subset selection using this prediction of sales from advertising. And this is something we've looked at in previous lesson videos. So we're trying to predict sales. We have 3 different advertising domains that we can spend, that different companies have spent money on in different areas, in different regions. And so people spend money on TV or radio or newspaper advertising. And so we want to predict sales as a linear combination of these different advertising amounts, doing our linear regression. And so each row corresponds to a different model. So that first row corresponds to a model that has just TV in it. The second row is a model with just radio. The next row is just newspaper. And these X's tell us which different regressive variables are being used. And so the next row has TV and radio in it. And so that's a regression model with TV and radio. In this column, the 4th column, we have the F statistic. And so that is some measurement of how good of a fit we have relevant to the number of regressive variables, or how good our model is. This is useful for comparing nested models, but it's not useful for comparing, or not appropriate for comparing models that aren't nested. So we have some F statistic numbers here that we've used in a previous video. What we really want to do here for comparing the different models is look at the AIC, Akaike information criteria, and that gives us a better measurement, a better statistic for comparing linear regression models when they're not nested. Nested means one model is a subset of the other. One model contains a set of variables, and the other model contains those set of variables plus other variables. And so this AIC column is really what we care about more than the F statistic. And we also care about this cross-validation root mean squared error column. Okay, so the better models have a lower AIC and lower root mean squared error. And as you've probably already identified, marked in red the best model and orange the second best model. So here's the best one and second best. It's useful to note that the best has an AIC of 780. The second best is really close at 782. It's really telling us we need TV and radio, maybe newspaper, maybe not. When we look at the error from cross-validation, the best is at 2.91, second best is at 2.95. It seems like TV and radio is all you need, but it's not horrible to add the newspaper either. So that's different ways you could quantify that. This is a good example of model selection. We've gone through all possible linear regression models here, all possible subsets of the regressive variables that could be used in the model. And we've looked at the AIC value for all of them, and we found the best, and we also observed that there's a second best that's almost as good as the best. And so this is all that model selection is. You want to look through possible models and pick the one with the best criteria based on some criteria that you set beforehand, AIC or cross-validation error. There's a couple other metrics we could use. And so here's the sketch of the process of subset selection, right? Just as we were saying, you want to search through all possible models. and get the set of predictors that give us best results. And best results could be lowest cross-validation or some test statistic. And so on the right-hand side on the slide, we have a bunch of different test statistics that could be used. You could use an adjusted R-squared. You could use an F statistic that's really only useful for predicting nested models, so we don't want to include it, right? If you notice in our list here, F statistic isn't listed because we don't want to use it for comparing non-nested models. You could have adjusted R-squared or CP or BIC, that's Bayesian Information Criteria, or AIC that we've talked about. If you look at these three in the bottom, they all have a similar structure. The first part has a goodness of fit term. RSS is residual sum of squares. That's your sum of squares error. And then after that, there's a second term, which is a penalty on the model size. Remember here, K is the number of predictors or number of regressor variables in the model. So if K were 2, we'd be trying to predict our output based on 2 input variables. If K is 10, we have 10 input variables. So all of these three methods we have here for measuring the goodness of a model is all always some goodness of fit, and then we penalize based on the model size. And the idea is when you take a larger model, meaning more predictor variables, you'll always get, as you add more predictor variables to your model, you will always get decreased error. So you want some penalty for adding those predictor variables that penalizes for adding those. Okay, so here's a formal write-up of the model space search of a way you could do that. So you start with the null model, and then for each K, meaning one element, we're going to look through one element models and 2 element models all the way up to the P element models. You do steps A and B here. And so you fit all the models that have that number of predictors, and then you can pick the best among these. Since we're picking in this step 2 between models of the same size, meaning the same number of predictors, you just need to use residual sum of squares error or an R-squared. That's fine for comparing models of the same size. It's a little faster than computing BIC or AIC or CP. So you would use those to compare among the models of the same size. And then once you've chosen all of your models' best fit model within each size, right? That would be MK. You compare among all those M's, and now we're comparing models of different sizes, not generally nested, so you want to use one of our metrics here, CP, AIC, BIC, or adjusted R-squared. Now, there's a problem with this method. If we're looking through all K values, for each K we have P choose K models. In the end, we have 2 raised to the P number of models to check. Now remember, P is the total number of input variables you're considering. So if you have 25 input variables you're considering, then this is a total of over 33 million regression models. So this takes too long to run in practical time. If you get very many more predictor variables than that, it becomes literally impossible to run in a human lifetime. So we need some way of searching through all possible models, but we're not going to search through all possible models. We're going to search through some of the possible models and try to find the best fit without having to search all of them. Okay, so this process of searching through some of them, there's a number of different ways you can search through models to find the best. Generally, we want to find a model and then try to modify it to find a better model, and then modify that to find a better model. Sort of a gradient descent type method. And so the first method for doing this on the left-hand side is called forward stepwise selection. These 2 algorithms are looking at our stepwise regression. So we start with the null model, meaning there are no regressors, and then we try adding a regression variable and trying the best model by adding 1. And then we add another regression variable to that and see how we can improve adding another regression variable to that. And then we add another one and we grow our models bigger and bigger as we go along. The other method here is called backwise stepward selection, and it works in the reverse order. So we start with the full model. That means we're going to start with all our regression variables, and then as we iterate, we first remove the least effective regression variable and see if we can get improved performance. Then we try removing another variable and improving performance and go down. Really the best way to go is something that's a hybrid search. Usually you start maybe with the null model and you build up for a while till building up doesn't help, and then you try to build down and try to remove some variables and then build up again. So you're stepwise adding and subtracting regression variables trying to improve your model. Here's some plots of searches for good models. And so in all of these examples, we're trying to predict the best regression model, or the number of predictors predicting defaulting on loans in the credit data set. Right? Here's the credit data set. So on the x-axis in each of these, in the top row, we have the number of predictors, actually number of predictors on the x-axis in every plot. On the y-axis, we have some statistic that's used for measuring how good of a model we have. And so this is walking through the process that we looked at 2 slides ago, this process right here, this best subset selection, where you search through every model size and you try to pick the best model in each model size, and then we compare among those using some criteria. So that's what we're doing here. We've gone through for models with 2 predictors, 3, 4, so on, number of predictors, and we in each of those sizes, 2, 3, 4, up to 10, 11, we look at the best model of that size, and then we compute the statistic for it. And so when you're using CP, that's predicting that we get the best model as a size 6. This X shows us where the best model is for this method of testing comparing our models. With BIC, we get a model of size 4. And with adjusted R squared, of course, is higher is better, closer to 1. I'm not quite sure. It's about a 6. And so one of the things you'll notice here, BIC has a slightly smaller model. BIC prefers small models in comparison to the others. And when you go back a few slides to the formulas, here's BIC. The term here penalizes more for when you have a large number of regressor variables. This natural log of n is sitting in the place of a 2 in the other methods we have here. And so natural log of n is the total number of observations, so that can get big and tends to penalize large models more, or puts more of a penalty on the model size. So BIC tends to get smaller models. That doesn't mean that it's better or worse, it's just worth knowing as part of the characteristics of these different methods. On the bottom row, we're going to compare the BIC model selection to cross-validation. And so the BIC says the best model is size 4, but if we talked about you don't have to use these methods, you could use cross-validation to pick among the different models. And so validation set error and cross-validation gives us models of size 6. So review, we've talked about model subset selection, and that's a process of selecting a good subset of our predictors. Often when you're given a linear regression model with a large number of predictors, some are useful and some are not useful. So it's important to remove the not useful ones. And so this improves prediction accuracy, model interpretability, and statistical inference. The process of model selection involves searching through all models or some stepwise search through some models, choosing the best models based on either cross-validation error, adjusted R squared, CP, BIC, or AIC. Thank you very much for watching.